Now we're going to finish up our study of labeled combinatorial classes by talking about mappings. A mapping is a very simple concept. A mapping is an n-word of length n. So it's a function from the integers 1 through n onto itself. We just list all possibilities. And it's pretty clear that the number of mappings is going to be n to the n. For every position, we can assign any one of n different numbers. It's n to the n. That's simple enough, but actually there's an underlying structure that's fascinating and related to numerous applications, arises in numerous applications. So a mapping is a function from the set of integers from 1 to n onto itself. And so here's an example of a long mapping where I have the numbers 1 through 37, and then down below I have the numbers 1 through 37. And they can appear multiple times. That's a mapping. Each one just has to be some number between 1 and 37. Now what's interesting is you can use a directed graph structure also to describe mappings, and they expose the combinatorics of what's going on maybe better than the tabular structure. So for example, 27 goes to 20, and then 20 goes to 9. And then 9 goes to 26, and 26 goes to 1, and 1 goes to 9. This is a special case of the sets of cycles that we had for permutation, but it's a set of more complicated structures that this directed graph illustrates. There's natural questions that arise and that are actually important in applications. Like what's the probability that it's connected? Or how many different components are there? How many nodes are on cycles and how many are on trees. And then there's parameters of mappings that we'll talk about next time is like what's the average time it takes to get from a node to its cycle? What's the average size of the cycles? All of these questions are of practical interest. And analytic combinatorics, again, handles them all in a uniform way. So let's just look at enumeration. How many mappings are there of length n? Again, if we go like we did for trees, we can look at different ways of labeling the different structures that might come out. And again, now there's definitely plenty of complications in the number of different structures there are. There's only one way to label that one, just 1, 2, 3. Or another way to look at it is just list out all the 27 mappings and then see what the structure looks like. So 1, 1, 2, so that means 1 points to itself, 2 points to 1, and 3 points to 2. But that's also the same as 3, 2, 2. That's where 2 points to itself, and 3 points to 2, and 1 points to 3. So those are all the different ways to label that structure. And there's 6 of them, 2 of them. And again, this complicated labeling and this complicated set of structures adds up to this simple result, n to the n, by correspondence with n words. But this internal structure is definitely of interest. So with the analytic combinatorics, we're going to be able to take that apart and understand properties of the structure, which is important in applications. Now, in order to do this, we're going to need a powerful tool known as Lagrange inversion. And it actually is useful for the study of any tree structure, and it's a very deep theorem that has many applications in mathematics. We're going to use it in a pretty straightforward way, but anyway, it's necessary to state it. I'm going to leave out the proof because it's best understood via more advanced techniques than we're going to cover in this course. But anyway, here's a statement of the so-called Lagrange inversion theorem. So the idea is it's about the inverse of a function. So I have a function f of u equals z, then its inverse is the function u equals g of z. So for example, if f of u equals u over 1 minus u, then solve for u, and that's g of z equals z over 1 minus z is its inverse. So the Lagrange inversion theorem says that it gives a way to get the coefficients of g from the form of f. So it says that if you have a generating function that satisfies the equation z equals f of g of z, so that's the inverse definition. And these conditions that f is 0 and f prime 0 is 0 and f prime 0 is not 0, then the coefficient g sub n is 1 over n times the coefficient of u to the n minus 1 in u over f of u to the nth power. And that's what it is. So in our simple example, where f of u equals u over 1 minus u, then the theorem says that the nth coefficient, the generating function for g of z, is 1 over n, coefficient u to the n minus 1, in 1 minus u to the n, because u over 1 minus u is 1 minus u to the n. Coefficient of u to the n minus 1 of that is minus 1 to the n times minus 1 to the n minus 1, and divide by n, we get minus 1 to the n minus 1. And that's exactly what g of z is, z over 1 plus z. So you can study this and learn about inverses, but really we're going to be applying this theorem in pretty much a cookbook fashion, symbolically, just like this. So from the point of view of analytic combinatorics, it's an analytic transfer theorem that gives us coefficients once we know a generating function, because in recursive structures like mappings and trees, we often encounter generating function equations like this. In fact, we use a more general formulation called the Berman form of the Lagrange inversion theorem. And that's if we've got another function, h of u, and we want the coefficient of h of g of z, then we put in h prime, and it's just generalizing the basic theorem from h of u equals u. And so this is the form that we're really going to use for mappings. And again, this is a deep and wonderful theorem that I don't have time to do anything more than state for you so that you can understand how we extract coefficients. Just as a classic application for Catalan numbers, this is with OGS that we did last time. A binary tree is a node or two binary trees. This is counted by external nodes, so we have that OGF equation. Rewriting that, it's z equals t of z minus t of z squared. So that z on the left-hand side, that makes this a candidate for Lagrange inversion. The theorem says if we want the coefficient of z to the n in t of z, we're just going to take f of u be u minus u squared. So we got z equals f of g of z. U minus u squared, t of z minus t of z squared. So we took f of u equals u minus u squared, so we want u over f of u. So that's u over u minus u squared, that's 1 over 1 minus u. So we have coefficient of u to the n minus 1 in 1 over 1 minus u to the n. Use the standard generating function for 1 over 1 minus z to the m, we get the Catalan numbers out. So that's a classic application of Lagrange inversion. And we can use it for other types of tree structures. We get other types of f of u, and the same method is going to work. And we'll look at it from a general point of view later on. But now let's look at Cayley trees and mappings. So Cayley trees are labeled, rooted, unordered trees. They're a special case of mappings where every node points to just one node and there's one root and it's connected. So the construction is simple. A Cayley tree is a tree connected to a set of trees. The transfer theorem then gives us immediately C of z equals ze to the C of z. That's the exponential generating function for Cayley trees, labeled, rooted, unordered trees. And so that means that z equals C of z over e to the C of z. So that means we can apply Lagrange inversion with f of u equals u over e to the u. C of z over e to the C of z. And so that's Lagrange inversion, u over e to the u. U over e to the u is e to the u. So the number, coefficient of z to the n is 1 over n, coefficient of u to the n minus 1 in that. That's coefficient of u to the n minus 1 and e to the un. Well, e to the un, that's sum of k factorial, un to the k over k factorial, coefficient n minus 1 in that is n to the n minus 1. So the number of Cayley trees with n nodes is n to the n minus 1. So that's a direct proof with analytic combinatorics. Now, it does depend on Lagrange inversion, but Lagrange inversion is a very general tool that we can use in this same way for many similar problems. So that's Cayley trees. Now, it suggests some kind of bijection between Cayley trees in words with n minus or in mappings with constraint on it, but that's actually one of the classic problems in combinatorics, is to find a simple bijection. Okay, so now what about mappings? Well, let's move one step up. So a mapping is got cycles of Cayley trees. So that is, you have a Cayley tree and then maybe the root node is on a cycle, or maybe it's a single cycle of itself. So that's connected components in mappings. So, or this is how many cycles of Cayley trees are there. Again, so these are just one connected component. Those are the mappings that have just one connected component. So there's one of size 1, 3 of size 2, and 17 of size 3. So it's labeled cycles of trees. And those are all the ways to label that and so forth. So the answer to that is more complicated. And so let's look at it from the standpoint of analytic combinatorics. So here's a cycle of Cayley trees. So you take a cycle and then take a Cayley tree going into any element on the cycle. So that's just an example. It's a special case of a mapping. But the construction is simple. A component is a cycle of Cayley trees. And then the transfer to generating functions is simple. The exponential generating function for cycles of Cayley trees is log of 1 over 1 minus C of z, where C of z is the exponential generating function for Cayley trees. Now, what about extracting coefficients? Well, here's where the Berman form of Lagrange inversion comes in. We still get to use u over e to the u, but now we have this other function, h of u, which in this case is log of 1 over 1 minus. So coefficient of z to the n in log of 1 over 1 minus C of z, where C of z equals u over e to the u. You just plug into the formula and take so h of u is log of 1 over 1 minus u. We're supposed to use h prime, so that's 1 over 1 minus u. And then the u over f of u to the n is e to the un, just as before. So to find the number of cycles of Cayley trees, its coefficient of z to the n in y of z is 1 over n coefficient of u to the n minus 1 in that function. And that one is a convolution, because we've got 1 over 1 minus u times e to the un, so it works out to that convolution. And then this is just changing n to n minus k, and then the thing that we want is n factorial times coefficient z to the n and y of z, and that comes out to this expression here. And this is a well-known function known as the Ramanujan Q function, and you can look in part 1 of the course to where we talk about the asymptotics of that function. And we'll also talk about asymptotics of this again when we get to complex asymptotics in the second part of this course. So this problem doesn't have so simple an answer, but it indicates the structure that lies underneath this. And then what we really want to finish the job is the number of mappings. How many different mappings are there? A mapping is a set of cycles of Cayley trees. Couldn't be simpler. And then the equation is a cycle of Cayley trees is log of 1 over 1 minus. A set of those is e to that power. So we just get 1 over 1 minus c of z. Again, that's ripe for use of Berman form, where now we use the h function is 1 over 1 minus u, and then f of u equals u over e to u as before. So now the derivative of h is 1 over 1 minus u squared. So it's the same as on the previous slide, except we have a 1 over 1 minus u squared times u to the n. And then if we do the convolution that time on this one, then we get seems like a slightly different form of it, but actually this one kind of telescopes and gets to the answer n to the n over n factorial. So the end result is the number of sets of cycles of Cayley trees is just n to the n. Quite surprising that we get down to that simple result, but we have a clear explanation of all this structure through the analytic combinatorics. And that's extremely important when we come to analyzing parameters of these structures. That'll be the subject of the next lecture. So that's an introduction to mappings using analytic combinatorics.